Jonathan, may I ask a philosophical question? Isn't it possible that these brains that evolved to survive and procreate in a very specific environment are simply incapable of understanding these things? And our impulse to latch on to a particular explanation is an evolved reaction to the mystery of life?
My brain is not incapable of understanding these things. I have no problem. Look, you never know. I don't even know how you would ever know if there was some feature of reality that was literally impossible for us human beings to understand. What I do know is that we've understood an enormous amount about reality. It's been less than a century since the Solvay conference and the first strict formulations of quantum mechanics, and we've gone enormously far. To me, if history is telling us anything at all, it's not that we're about to bump up into fundamental limits, it's that we are pretty darn awesome at understanding reality.
So towards the end, you gave a brief overview of the relationship between geometry, entanglement, and energy. And one of the questions I have is, classically we know, we mentioned it early in your lecture, that if you have two particles, two photons, let's say, and you entangle them, isolate them perfectly and separate them across the universe, those two particles, the moment you detect them, the entanglement relationship is conserved. How does that fit into this geometry and entanglement picture? Because you stated earlier, and I know this is a bit of a overview of the topic, that we can describe close, like highly entangled particles as being close together, but if you separate these highly entangled particles across the universe, they still follow that relationship.
Yeah, this is, I feel like I am not obeying my own advice here, because this is a question I get, or a version of it, every single time I give this talk, so I clearly need to do better at explaining it in the talk. But the point is that the entanglement we're talking about here is the entanglement between regions of empty space. It's not the entanglement between particles. Particles are something extra, something over and above the region of empty space. So if I have a little box, a cubic nanometer or whatever, and I have a particle in that box, that means that one of the quantum mechanical field modes is vibrating. But the overwhelming majority of the quantum mechanical field modes are still in their vacuum state. So even in the middle of this room, even in the middle of a neutron star, as far as quantum field theory is concerned, it's almost empty space. Almost all of the quantum fields are still in their vacuum state. So in terms of calculating the entanglement between one region of space and another, the fact that there's a particle there, two particles that might be entangled, is entirely irrelevant. The regions of empty space are still doing most of the entangling. So the point of the question is that if I have two particles, there's zero relationship between their entanglement and their distance from each other. The relationship only exists for regions of empty space.
I think you might have just answered my question, but I'll ask it anyway. Is entanglement a binary, or is it a spectrum? As in, are you entangled or you're not entangled? Because when I think about quantum computers, they go through great lengths of entangling particles. But here we talk about highly entangled versus not very entangled, so it seems like it's a spectrum.
It's 100% a spectrum. That was a good one.
Can I ask
Yeah.
or try to put together two questions from online about time? So, and I'll preface it, the Schrodinger equation describes how the wave function changes in time. But their questions are concerned with the past, the present, and the future, and the fact that time only really seems to go in one direction. So can you, can you comment
about that? Yes, can I comment? Sure. This is a whole separate talk. Maybe I'll come back and give it some other day, about why is there an arrow of time in the universe. The arrow of time is simply the fact that the past, present, and future are very different from each other, manifestly so. I have photographs on my computer. Here's one. This is a photograph of my cat Caliban, but it's a picture of what he looked like in the past. There are no pictures of what he looks like in the future. I have different epistemic access to the past and the future. That's so blatantly built into our experience of reality that we take it for granted, but the fundamental laws of physics whether they're Newton's or Schrodinger's or Einstein's, do not differentiate between the past and the future. Why do we have this manifest difference in the real world? The answer is something called the second law of thermodynamics. Entropy increases over time. Entropy is a measure of the disorderliness of the universe. It is true that we think it is true, we hypothesize that it is true, that there's some fundamental law of physics that says how the state of the universe exactly specified evolves with time, but you and I don't observe the exact state of the universe. We observe some features of it. Here in this room, there are air molecules. They bump into each other, but we don't see the air molecules. We see some coarse-grained features of temperature and density and so forth. So given that incomplete knowledge of the state of the world, there's a feature that the universe started in a very orderly state, low entropy, and that entropy is increasing over time. And I wrote a whole nother book called From Eternity to Here, which will explain to you why that increase of entropy over time accounts for why we can have photographs of the past but not the future.
Hi, Dr. Carroll, I'm Jeff. I want to ask a question about many world interpretation. So I think, so correct me if I'm wrong about understanding the interpretation. In many world, we, in each of the branch, the world seems to be classical to us because every single moment when there's superposition, it splits. So how do we measure the interference of electron in one world, one of the branch we are on?
Right, good. This is a great question. It's actually like crucially important to understand, but we do mostly understand it. Why is it that on the one hand, when we open the box, we see the cat awake or asleep? We never see a superposition. But on the other hand, when we look at electrons, we do see them in superposition. The rough answer is because cats are big. And what that means is you cannot shield the cat from becoming entangled with the environment. The photons and the air molecules in the box are continually banging into the cat because it's a large macroscopic object, and that is decoherence. That is exactly this process that we saw here. But a single electron you can shield from interacting with the environment. You can keep it from bumping into air molecules. What we're trying to do in quantum computing is build larger and larger quantum systems that you shield from decoherence. Very hard to do because every photon could mess you up. Any warm object emits photons in the infrared. That's why your quantum computers have to be really, really super duper cold to prevent them from decohering.
I wonder if I could take you back to the discussion of the arrow of time for a moment. Maybe you put the branching new world.
Sure.
Because the remarkable thing about that to me, or one obvious thing about it, is that it's highly asymmetric in time. And based on your answer just a couple of moments ago, you suggested that that's essentially to do with the second law of thermodynamics. But could you make that connection a little bit clearer here with reference to this diagram? Are those branches psychological in nature? And I'm just asking to say a bit more about that.
Yeah, so it's a great question. There's absolutely, even though the Schrodinger equation has no arrow of time in it, this picture clearly does, even though I told you that the picture was just, that the whole theory was just the Schrodinger equation taken seriously. Well, the answer is you also need to have an initial condition for the universe, and for reasons that we truly do not understand right now, the initial conditions of our universe were very special. They're very special in a way that can be quantified into saying that the entropy was very low. There's different definitions of entropy depending on whether you're talking quantum mechanical or classical, but in every way, the universe was simple and very, very organized at early times. That's reflected in this picture by seeing that there's just one big quantum state at early times and many, many complicated things later on. So we don't know why that's true, but you need it to make it work. Eventually, by the way, it will go away, right? We live in this world right now in the middle of the evolution of the universe where classical physics seems to be a pretty good approximation. This is a temporary condition. Just like if you mix cream and coffee, they will eventually equilibrate and become maximally mixed. Eventually, you'll branch the wave function of the universe as much as you can. And when that happens, there will be no distinction between one branch and another. Classical reality will no longer be a useful approximation to talking about the world. In terms of psychology, that's not quite the right way to say it. There's an emergent pattern here. There is something that works about describing parts of the universe using a classical approximation. That is not just psychological, that's a true, real pattern in the universe. We're just taking advantage of it.
Do you think that Bohmian mechanics could also be a kind of fundamental or like a kind of an emergent interpretation from just quantum mechanics, or do you think there's too many assumptions with that as well?
Yeah, if you remember back when we talked about the reality problem, I forget where it was. Is the wave function the only part of reality, or are there other variables or physical quantities in addition to the wave function? So there is an approach to quantum mechanics, the foundations of quantum mechanics, that says the wave function is real. It explains why electrons behave like waves when you're not looking at them. But there's another set of physical variables that are also real. The positions of particles, in addition to the wave function. And the reason why you see particles when you look at electrons is because you're seeing the particles. You're not seeing the wave function. And the role of the wave function in these theories is to guide the particles around, to push around the particles right and left. This is called Bohmian mechanics. I think that there's zero interest personally in it from me, because I think that many worlds works really well. Why make it complicated? But other people disagree.
I had this question. So in one of my, when I was taking the general relativity course here at UMich, I learned about the holographic principle, which is the idea that if you have a four-dimensional space-time, the information about a region in that space-time can be encoded on a three-dimensional boundary. When you try to derive general relativity from quantum mechanics, as you have said here, based off of entanglement, you get a similar idea where the entropy would impose a constraint on the geometry.
Well, we don't know, is the short answer. In the approach that I was talking about in deriving space-time from entanglement, this particular version only is worried so far about situations where gravity is very weak, like here in the solar system where you have planets and stars and things like that. When gravity becomes strong, when you have a black hole or the whole universe all at once, different features kick in that can separately be described using ideas like holography and complementarity. Those are not things we're worried about here yet. We would like to get there someday.
Hi, my name is Matthew. I had a question about this, actually. I was a little confused. What's the difference between the entanglement that gives rise to geometry and the entanglement between two distant particles? It sounded like there's two different kinds, but I thought entanglement is entanglement.
Entanglement is entanglement, but in quantum field theory, most of what is going on in any physical situation is the empty space part of it. So even when you have a particle, that particle is surrounded by many other vibrations in quantum fields that are in their lowest energy state. So particles are little tiny annoyances built on top of this huge number of quantum mechanical fluctuations in empty space. Therefore, it's that much more numerous set of fluctuations that we consider here.
Hi. I'd just like to ask for a clarification real quick. When you were talking about the idea of entanglement as a spectrum rather than a binary, is the idea that you're trying to get across that if we have something that is only like two particles that are only partially entangled, and you measure one of the properties on one of those particles, you have a probability of knowing that equivalent property on the other particle? Is that the idea?
That is exactly right.
Okay,
you
cool.
got it right. We've learned something. I felt like I did my job. Thank you very much.
Well, then let's thank you very much.